Chapter 13 is on benzene and its derivatives. Aromatic compounds were originally named because some had nice aromas, such as vanilla, cinnamon, and wintergreen. All contain aromatic compounds. An aromatic compound is one that contains a benzene ring. This is the structure of benzene. Its molecular formula is C6H6, and it's put together in a cyclic fashion. Benzene is toxic. If you drink the liquid, it is poisonous. Exposure to the vapors over time causes cancer and liver damage. Benzene is used in many industrial processes to make soap, pharmaceuticals, pesticides, and many other compounds. Aliphatics is a name given to hydrocarbons that are not containing a benzene ring, such as alkanes, alkenes, and alkynes that we previously learned about. Below are three examples. Let's do a review on naming them. The first one here is an alkane because it has all single bonds. There are 6 carbons in a ring, so the name would be cyclohexane. The next one is drawn as a condensed structural formula, so that again implies that every angle would represent a carbon, and then we'd have the appropriate number of hydrogens attached to each one of those carbons, so it has 4 bonds. So to name this, we have our 6 carbons in a ring, so it would be cyclohex, and then the ending is -ene because we have a double bond. The one at the end has a triple bond, so that is an alkyne, and there are 3 carbons, so that would be propyne. Aromatics, again, are compounds that contain a benzene ring, and this is benzene. You need to know the structural formula for that. And aromatics contain benzene. They are also a functional group. So you can have more than one functional group in a compound. This is the condensed structural formula for benzene. So that would be a functional group. We could call that aromatic. Sometimes people just want to say benzene is fine as well. The other functional groups we can find in this compound is a carbon with a double bond to oxygen and then attached to a hydroxyl here. That makes that a carboxylic acid. The other functional group that we'll find here is a carbon attached to an oxygen and another carbon and a double bond to an oxygen. That makes a carboxylic ester. We know that aromatics are different from aliphatics. Benzene does not actually have 3 single bonds with alternating 3 double bonds. It's more like it has 6 1.5 bonds between those carbons. How they know that is you can actually measure the bond length between the carbons in benzene and find that the length is somewhere between a single and a double bond. So we learned previously that a single bond is longer than a double bond. So they can actually measure with powerful microscopes the distance between these carbon atoms. So if this was a single bond, it would be about this distance. The distance for the double bond would look like this. For benzene, that's not the case. When they measured the distance between the 2 carbon atoms, what they found out is the distance was somewhere between a single and a double bond. So they determined that that is a good way to draw the structure, but it's not really the best representation. So benzene can be represented as a resonance structure. A resonance structure is a combination of 2 structures put together, which is represented by this double-headed arrow here. It's like a hybrid, 2 things combining. So we have this almost exactly the same as just the position of our carbons have been alternated. So the way benzene is often represented is with 6 carbons in our ring, but a circle drawn in the center. So that's more accurate to show you that the bond length between all those carbons is actually equal to each other. So you will see benzene either written as this resonance form or as the alternating single and double bond format. So a hybrid, again, is a combination of two things. So you can think of benzene as a hybrid, just like a Prius is a hybrid. It's a combination of a gas and an electric motor. Another example of a hybrid is a mule. A mule is a cross between a horse and a donkey. So you can think of benzene as a hybrid as well. We are going to learn how to name benzene derivatives. Our first rule is if you have just one group attached to a benzene ring, you're going to name the group that's attached and then add the word benzene. So for our first example here, we have Cl as our group that's attached, so that would be called a chloro. And then it's attached to our benzene ring, so the name of this compound would be chlorobenzene. The next compound we have a CH2, CH3, that is called an ethyl. It's attached to a benzene, so the name of this compound would be ethylbenzene. Name the following benzene derivatives. The first one here, we have a propyl group attached to benzene, so the name of the compound would be propylbenzene. The second compound, we have an I attached, and I would be called iodo. So this is iodobenzene. This slide shows the common names of 4 benzene derivatives. I do want you to learn these names. These common names will be used to name these compounds and can also be used to name the parent instead of using benzene. The first one you have is a benzene with a CH3, which is called methyl. So the name is not going to be methylbenzene. You need to remember if you have a methyl group attached to benzene, the name is toluene. If I have a hydroxyl or an OH attached to benzene, the name of that compound will be phenol. If I have an NH2 or an amino group attached to my benzene, the name of that compound is aniline. If I have a carboxylic acid group attached to benzene, the name of that one is benzoic acid. So benzoic acid, again, you can think I have the carboxylic acid attached to it. That will help you with the ending, the oic acid. Amine starts with an A, so that might help you remember aniline has an amine attached to it. And then phenol, you're going to need to remember that one. That's a common name for this group here, and it's also a functional group that we'll be learning in our next chapter, chapter 14. So that's something that will be coming. So please remember these names of these benzene derivatives. Our second rule for naming benzene derivatives is when we have 2 groups attached to a benzene ring, you're going to use ortho, meta, and para names to identify where the groups are attached in place of numbers in your benzene ring. These are Greek words. Ortho means straight. Meta means after. And para means beyond. And that might help you remember the positions that they stand for. Ortho means 1, 2, and you could think of the groups being straight across from each other in positions 1 and 2. Meta means 1 and 3, so that would be 1 after 2. And para means positions 1 and 4, and that would be the one that's farthest beyond. So let's look at our example here. The first one, we have 2 bromines attached to benzene. So that gives us dibromobenzene. And then normally we would say the positions are at 1 and 2. But anytime you have two groups attached to a benzene, instead of using the numbers 1, 2, you're going to use that prefix ortho. The second one we have is, again, two bromines attached to benzene gives us dibromobenzene, and then we want to show locations. So these would be at carbons 1 and 3, but instead of using 1 and 3, we would use the prefix meta. The third example, we have dibromobenzene again, and we look at the location of those bromines. So that'd be 1 and 4 are the positions, and instead of writing 1 and 4, we would write para. One of my students in the past came up with a sentence to help them remembering ortho, meta, and para, and their sentence was, orthopedic mattresses feel like paradise. Like this cat looks like he's in paradise right here on this mattress. And again, the ortho is the first position, 1, 2. Meta is the M in mattresses, positions 1, 3. And then para, our last one, is positions 1, 4. So hopefully that sentence may help you remember, but please remember when you're using positions 1, 2, 1, 3, 1, 4 in your benzene with two groups attached that you use ortho, meta, and para prefixes. Name the following compounds. So these compounds both contain benzene. So the ending is going to be benzene. The groups we have in the first one are bromo. The other group is a chloro. So we want to put those in alphabetical order. So that would be bromo, chloro, benzene. And then we want to show where our groups are attached. So we're going to start with position 1 for our bromo. Chloro would be at position 2. And again, our rules say if we have two groups attached to a benzene, we need to use the prefixes ortho, meta, or para. And positions 1 and 2 would be represented with ortho. And then you put a dash between ortho and bromo because it's acting like the numbers 1, 2 for ortho. So the name is ortho dash bromo chlorobenzene. The second one here, we have a group attached. We call that methyl, and we have a group Br, which is bromo. Now, one of the things I asked you in this chapter, instead of calling that methyl benzene, if you have a methyl attached to a benzene, this is now called toluene, and this becomes our parent. Instead of using benzene as the parent name, we use the parent name toluene. And if this is the parent, that means the CH3 is going to be carbon number 1. And therefore, our bromo is attached at carbon 3. So to name this compound, it would be bromo toluene. And then the locations are 1 and 3, so that would be meta. So it's meta dash bromo toluene. Rule number 3 in naming benzene derivatives is if you have 3 or more groups attached to benzene, use numbers to identify where the groups are attached. So in the first example here, we have 3 bromos attached to benzene, so that's tribromobenzene, and then we go back to our numbering instead of using ortho, meta, and para. So our groups are at carbons 1, 2, and 4. So we get 1, 2, 4 dash tribromobenzene. The next compound on the right, we have again this methyl group attached to benzene. That becomes our parent. So the parent is called toluene. And NO2, we didn't learn the name of that group, but that's called a nitro. So this one is just here for an example. You don't have to remember that. But we have 3 nitros attached, so that would become trinitrotoluene. And then wherever the CH3, that's part of the carbon that's attached to our benzene ring, is going to be carbon number 1. So then we'll go ahead and number our other carbons. Okay, so then we end up with carbons number 2, 4, and 6, where our nitro groups are attached. So it becomes 2,4,6-trinitrotoluene, also known as TNT, that explosive material. Name the following compound. Let's start by naming the groups. So Br is bromo, Cl is chloro, and bromo comes before chloro in the alphabet. So we would put bromo, chloro, benzene. And now we have 2 bromos, so we're going to put a di in front of bromo. We want to show the locations of our groups, so we're going to start with carbon 1 at our bromine, carbon 2 the other bromo, and then carbon 4 is where our chloro is located. So in front of dibromo, we'll go 1, 2 dash dibromo dash 4 dash chlorobenzene. Name the following compounds. Let's start with the compound on the left. First is going to be identify our parent group. So this is one of the ones that is our benzene derivative with the common name, is we have a benzene attached to that carboxylic acid. So that is called benzoic acid. And the carbon that's attached to that carboxylic acid is going to be carbon number 1. So we're going to number the carbons in our ring so the groups get the smallest number. So we're going to go right to left in this case. And our groups are chloro and Br is bromo. So alphabetically, bromo must come first. So we have bromo, chloro, benzoic acid. And then we need to show the locations of our group. Our bromo is located at carbon 5, and chloro is located at carbon 2. So the name of our compound is 5-bromo-2-chlorobenzoic acid. The compound on the right, our parent is a benzene with an OH attached, which is called phenol. Then we have this group attached, and it's drawn as a line angle drawing, which again means every angle and the end of it represents a carbon. And then that carbon has to have 4 bonds. So I'm just adding that in so it's easier to see. The name of that group with 2 carbons is called ethyl. So this is called ethyl phenol. And then it's like we have 2 groups attached. So we're going to use that ortho, meta, para prefix. And we have groups at carbons 1 and 3, so that would be meta. So it's meta-ethyl phenol. Draw 2,3-difluoroaniline. So we're going to start with the parent, which is aniline. Aniline means that we have benzene. And I'm going to draw benzene with a ring in the center, or you could do alternating single double bonds. Either one is acceptable. Aniline means we have that amine attached. So we have a nitrogen with 2 hydrogens attached. And that's going to be carbon 1. So at carbon 2 and at carbon 3, we have fluorines. So I'm going to draw my fluorines attached. So that would be 2,3-difluoroaniline. If you have more than one functional group in your compound, benzene is going to be named as a group and not as the parent. The benzene, as named as a group, will be called phenyl, not benzyl. You'll use phenyl if you have other functional groups present. So this would represent phenyl. The line means this is attached to something else. This compound has two functional groups. We have our benzene ring, which we could say is our aromatic group. And then we also have an alcohol here. We have an OH attached to a carbon with single bonds. That carbon is directly bonded to one other one, so we would call that a primary alcohol. So this compound has two functional groups. So how would we name it? Well, we're going to learn in our chapter on alcohols how to name an alcohol, but to give you a preview, we have two carbons, so the prefix is eth in this portion here. This would be my parent. And the OL tells us we have an alcohol that ends in OL. So we'll learn how to name those shortly. The 1 means the location of the OH would be carbon 1, and this would be carbon 2. So this would be considered our parent. Benzene is sort of a secondary component. We're now going to name that as a group. And when it's a group, we call that phenyl. It's attached to carbon 2, so it's called 2-phenyl 1-ethanol. This example is just to show you have two groups in our compound, two functional groups, and that the benzene is named as a phenyl in this compound. Name the following compound. This compound has two functional groups in it. The functional groups are a double bond, so it's an alkene, and then we have that benzene ring. We can call that an aromatic. Okay, so if we have benzene as one of our functional groups, that is no longer going to be the parent, but that's going to be acting just like it's a group. So that would be called phenyl, YL. And then we want to name our parent. So let's draw the carbons in to our line angle drawing. We have 4 carbons. So the prefix is but, the ending is -ene to represent our double bond. We want to show where the double bond is located. So we can number our chain from right to left or left to right. We want to pick the numbering so the double bond has the smallest number. So that would be from left to right. So I'm going to erase the one at the bottom. The double bond is between 1 and 2, so we put a 1 in front of butene. And then we have the group attached to carbon 1, our phenyl. So it's 1-phenylbutene. The other thing with the line angle drawing and the zigzag formation, we can tell where the hydrogens are actually oriented. So I'm drawing my hydrogens in, and I have a hydrogen pointed up and one pointed down. So we can tell if this is a cis or trans isomer. The positions of the hydrogens here across my carbon double bond tells me that I have a trans isomer. So the name of my compound would be trans-1-phenyl-1-butene. Name the following compound. This compound has two functional groups. We have a benzene ring, so we can say we have an aromatic functional group. And then we have the benzene with the OH. That is also a functional group called a phenol that we will learn about in an upcoming chapter. So to name the compound, when we have a benzene ring as a functional group, when there's two or more, it's no longer going to be considered the parent, but just as a group attached. So that will be called phenyl with a YL. The parent in this case is phenol. That you need to remember, a benzene with an OH is called phenol. That's our parent. Now to name the compound, the parent is phenol. We're going to put the group's name or the child in front is phenyl. And then we want to show where the phenyl is attached to which carbon. The hydroxyl group is attached to carbon 1. The phenyl group is attached to carbon 2. Instead of saying this is located at carbon 2, we have two things attached to our benzene ring, carbon 1 and 2. We use those prefixes, ortho, meta, and para. 1, 2 would be ortho, going in front of phenyl. So the name of this compound is orthophenylphenol. Draw the structural formula for 4-phenyl 1-pentene. We'll start by drawing the parent. Pent means we have 5 carbons. And I'm going to bond those together. The ending pentene, ene, means we have a double bond, which is located at carbon 1. So I'm putting a double bond there. We have a group 4-phenyl attached, so we're going to count over to carbon number 4. And I'm going to draw a phenyl. It says structural, so I want to show every single atom and every single bond. So I'm drawing all my carbons. Phenyl is basically my benzene ring with alternating single double bonds, and then making sure carbon always has 4 bonds. I'm going to draw my hydrogens in. And there is my phenyl. Now, the last thing you always want to do in structural formulas is make sure carbon has 4 bonds. So I need to draw some hydrogens. For my first carbon, my second carbon needs 1 hydrogen. The third one needs 2, just to make sure carbon has all 4 bonds. Okay, so there is our structural formula for 4-phenyl 1-pentene. Polynuclear aromatic hydrocarbons are also known as PAHs. PAHs contain 2 or more benzene rings, with each ring sharing 2 carbons. For example, naphthalene has 2 benzene rings attached together. Naphthalene is found in mothballs. The structural formula shows us that these 2 carbons here are shared between the 2 benzene rings. The sharing of these 2 carbons is what makes this a polynuclear aromatic hydrocarbon. Polynuclear aromatic hydrocarbons containing 4 or more benzene rings were the first group of compounds discovered to be carcinogenic. A carcinogen is a compound that causes cancer. About 200 years ago, they discovered in chimney sweeps that they were developing scrotum cancer. And this was due to their exposure to a compound called benzopyrene, the structure is down below, that's found in the soot or the ashes in the chimney. Benzopyrene is also found in cigarette smoke, which we know causes lung cancer, and in car exhaust, I would say in older cars that are emitting exhaust that looks like that. Phenols are a functional group. A phenol is when we have a hydroxyl or an OH attached to an aromatic ring. So we learn to name when benzene has OH attached to it, it's called phenol. But phenol, again, it can be a functional group, like in this compound here. We can also practice how to name this compound. So the parent would be phenol, our functional group, and then we have a Cl or a chloro attached in front of it, so it'd be chlorophenol. And then we want to show the location of the chlorine. The OH would be carbon 1, chlorine would be 2, and when we have groups attached to position 1 and 2, we use the prefix ortho. So that would be orthochlorophenol. In 1867, Lister discovered that phenol solutions in a dilute solution kills bacteria. So it was used as an antiseptic for surgery. And this was a huge discovery because prior to this, the surgery would be successful, but the patient might end up dying due to bacterial infections. So by having an antiseptic, a lot more people were able to live after surgery. Phenol is no longer used on patients because it's very corrosive and it burns the skin. But it is still used, however, to disinfect surgical equipment. Name the functional groups in methyl salicylate. This is also an antiseptic. It's a non-toxic antiseptic, and it's found in wintergreen. It's the oil in wintergreen. So the functional groups we can see here is we have phenol, and this angle represents a carbon. So we'd have a carbon with a double bond to oxygen, attached to an oxygen and another carbon. That makes that a carboxylic ester. Name the functional groups in caffeic acid found in coffee. So again, we have phenol, and we have a double bond. Again, every angle represents a carbon here, so that's an alkene. And we have a carbon double bond oxygen attached to an OH, gives us a carboxylic acid. Some of the chemical properties of phenols include being a weak acid and they are easily oxidized. The pH of a phenol is 5.4. Sometimes my students think phenols are an alcohol because they see the OH here and they will call that an alcohol. But just as a reminder, an alcohol, the carbon that's attached to the OH, must have all single bonds. There's a double bond here, so that cannot be an alcohol. So I'm going to cross that off. And just to show you based on physical properties, the pH of alcohol is 7. So it's neutral, versus phenols, the pH is lower than 7, so therefore it's an acid. The other thing we said is phenols are easily oxidized. So phenols are added to foods as an antioxidant. They prevent your food from being oxidized by the air. So we have two examples below. So for example, vegetable oil, they may add BHA or BHT to it because these compounds will cause the BHA or the BHT to be oxidized because they have phenol as the functional group in them versus the oil itself, or compounds such as oil are used in making potato chips. So instead of the potato chips or the oil going rancid from being oxidized by the air, which contains O2, the phenol will get oxidized first.